Hello students, in this video we will discuss the complexity of binary search. We will be discussing the time complexity. If you want to understand what is time complexity, then I have shared videos previously and I will be adding the link of the same in the description box. And for binary search, the complexity can be calculated in many ways. So let us look at one of the methods. So as you can see here in this picture, this is the intuitive explanation of the complexity of binary search. Later on in this video, I will be discussing the calculation using the substitution method of recurrence relations. So let us look at the intuitive method. Suppose you have these elements 7 nodes in the array with array consisting of 2, 4, 6, 8, 10, 11 and 14, and we are searching for the number 28. Now these 7 nodes, for these we will add 1 plus 7 divide by 2. If we will take index 0, then we will take 6 here, and since I have taken 1, so we will add 7 and divide that by 2, so we'll get 4. And if we take 0 plus 6, we'll get 3. But ultimately the same element will be referred in both the things, because in 0, 1, 2, 3, third index element is the fourth element, and 1, 2, 3, 4 is the fourth element. So we will be referring to the same element whether we take lower bound 0 or 1. So then we will look either in the upper half or in the lower half. So if we look in the lower half, we'll calculate mid as 1 plus 3, and then again we will further keep on calculating the mid depending on whether we are looking in the lower half or the upper half. Now if we look at it in an intuitive manner, now this is like a binary tree where each node will have 2 children. So if there are n nodes, maximum n nodes can appear here as leaves. So if we have not n nodes, but we will have maximum n nodes in the tree itself. So there are n nodes in the tree, and the depth of the tree, whatever it is, if we raise that to the power of 2 minus 1, then that will give us the total number of nodes in the tree. This we have studied already in the binary tree video, in which the introduction of binary tree was given. So you can refer to that video. So using this formula, so we have 2 raised to the power of depth of the tree is equal to n plus 1, which is the total number of nodes in this particular tree, plus 1. Now we take log both sides. So we have depth into log 2 and log 2 of n plus 1, and then depth is equal to, we keep this depth here and we take this log to this side, and so we get log 2 of n plus 1, because log of 2 is 1. So therefore depth is equal to log 2 of n plus 1, which is the complexity of the binary search algorithm. So this is the intuitive way, and the decision method is also based on this particular intuitive method only. Now let us look at the substitution method. For the substitution method, we need to formulate the formula for the binary search, the recurrence relation for the binary search. So for that we have T of n is defined in terms of T of n by 2, and since we will look at only one of the halves, that is either the lower half or the upper half, so it is appearing only once, and plus constant effort that is used for comparing the mid with the number. And therefore the total effort in the binary search is going to be the total effort in the T n by 2, that is the lower half or the upper half or one of them, plus the mid part where we are making the comparison. And what we have as the base case is T of 1, that is if there is only one element in the array, only one comparison is going to happen. So T of 1, that is for single element, the complexity is 1. Now what we will do here, we have this value over here where T of n is the time required for the binary search. Now T of n is equal to T of n upon 2 raised to the power of k plus 1 plus 1 plus 1. How we have achieved this? What we have done is we have iteratively substituted the value of T of n by 2 as T of n by 4 plus 1. So T of n by 2 is equal to T of n by 4 plus 1. Then again we substitute T of n by 4 as T of n by 8 plus 1. So ultimately what we are going to get is T of n upon 2 raised to the power of k plus these ones, these are going to appear k times. So we will have k as constant here. So this we have simplified. Now what we will do is we will put n is equal to 2 raised to the power of k, and therefore this relation is going to be T of 1. T of 1 we already know is 1 plus k. Now this k we will put log both sides. So what we will get is k is equal to log of n. So 1 plus log n is what we are going to get, and since log of n is less than equal to log of 1 plus log of n is less than equal to 2 of log 2n. So therefore what we say is that theta, that is the upper and the lower, both sides log of n is going to bind the function that we have defined, and therefore this is the complexity of the binary search method. Now I hope this video is useful to you and you are able to follow the complexity of binary search, and in the future videos I'll be discussing the complexity of other methods. Thank you very much.